fourth year PhD student. Oh, I see. It's the next one. It's all together. And it's here. You warned me about that. Come on. Am I pointing it right?
Oh, jeez.
We're going to get there. It's okay. There you go.
I did that.
Oh, okay.
I don't know what's going on.
Say click.
Yeah, that'll work.
Let me make sure. I guess. Yeah, it's on. All right. Well, at least we have a laser. Woo. Okay. This is me. I'm Maria. I'm a fourth year physics PhD student at the U of A, and tonight I'm going to tell you one of my favorite science stories. That is the discovery of pulsars and the subsequent process of figuring out what they were. And I love this story, not just because it is near and dear to what I study now, but also because I think it's a fun example of what happens when astronomers find something that they really weren't expecting, and then they have to figure out what the heck is going on. So, our story begins in 1967 at Cambridge University at the Mullard Radio Astronomy Observatory, where Jocelyn Bell, pictured here, is a graduate student studying with Professor Anthony Hewish, pictured here. And they have spent the last 2 years building a radio telescope that you can see part of in the back here. I'm not going to tell you what they built this telescope for. It's not really important right now. Spoiler alert, that is not what they found. So one day, Belle is looking at the readout from the telescope when she sees something strange. I'm hitting the button.
Oh, sorry, hold on.
That's okay. Something mysterious and exciting that you're about to find out.
Try again?
Yeah, good.
Okay, I clicked.
She sees what she calls a little bit of scruff. It's not that easy to see. If you click again, there'll be a little circle around it, in case it's difficult. I didn't know I didn't have a laser pointer. It is right here. It doesn't rise that far above the signal, and it looks a lot like this interference over here. But Belle says, I think I saw a little bit of scruff like this one yesterday at the same point on the sky. I think I might have seen one the day before that. And she thinks this is interesting and important, and she brings it to her advisor. And the first question that you have to ask when you see something new and exciting in astronomy is just, really? Because if we're being honest, more than 50% of the time when there's something unexpected, it means we hit the wrong button. Or picked the wrong number, or some of the neighbors did something weird that we weren't expecting. And that's basically what Hewish says. He says, never mind that. It's probably just some interference too. Just let it go. And for some graduate students, that might have been enough. But Belle has been working on this telescope with him for 2 years. She has laid over 120 miles of wire for it herself. And she has been the main person in charge of monitoring the readout night and day. So she probably knows this telescope much better than the back of either of her hands. And she knows what the interference looks like. She says, no, I know what I'm doing here. This is something. She convinces him that next time it comes around, they should go out and speed up the readout, which is essentially zooming in on that little piece of scruff. And what they find is this signal right here. Now, for anyone who can't see it, if you click again, there's going to be some lines just to help you see that it's a very regular pulse. This is not what interference would have looked like, at least not anything that anyone had seen before. It's incredibly precise. It's happening with the exact same time between each pulse, and it's so weird that it looks like it must have been on purpose. No one just created that by accident. And the signal originally gets nicknamed LGM1 because of this. So I have more than one trivia question for you tonight, but here's the first one. What did LGM stand for? Hands. Sorry, I forgot to ask for hands. Yeah, all right. One of the middle over here. Yeah, go for it. Yeah. D. Yes, correct. It stood for Little Green Man. The first thought was, oh my god, this is so amazing that this signal is out there. You can hit the next one. It just like makes it nice and bright. Aliens must be trying to get in contact with us. They must be trying to get our attention with this signal that doesn't look like it could actually be created by anything else. And this was a real possibility. It was really exciting. So then we had, the whole astronomy community had to go through the process of, okay, but is it really aliens? What else could it be? Figuring out what this mysterious blinking object is. And to do this, they're going to ask a few questions. And I'm going to keep a little box here with what they figure out so that you can help follow along. The first question that they asked was, how far away is it? Because, yeah, it doesn't look like any of the interference they were used to, but maybe it's something really weird. Maybe someone was playing around with a strange radar signal and decided to do something that made it bounce off the moon. This was a documented phenomenon. People accidentally bounce radar off the moon sometimes. So that was a possibility. And they just had to make sure that there's no weird stuff going on nearby on Earth, off the moon, in the solar system that might happen. So they did a measurement, and they attempted a measurement for the astronomers in the audience. It was a parallax measurement that they attempted to do that told them this was inside our galaxy, but outside the solar system. So there's no way that human actions or anything local had anything to do with it. And at that point, they can look at a list of candidates that are things that you could see blinking at you from very far away. So I have some of them here. We've got stars. The word pulsar originally came from pulsing star. Aliens, fan favorite. Already went through that. Who knows what they could be on? We don't know anything about the aliens or their culture. Finally, there's this category called stellar remnants. That's basically stars after they have died. And 3 objects there. We have white dwarfs, neutron stars, and black holes. You might notice I put an asterisk next to these last 2 and aliens, and that is because this was 1967, and all of these are theoretical at the time. No one's sure if aliens, black holes, or neutron stars exist. No one has ever seen one credibly. So, something to keep in mind as the search continues. The next question that Bell and Hewish asked was, how many signals are there? Because that little bit of scruff was really easy to ignore, and Hewish was about to ignore it. So if you go back and look at the readout, are there any more bits of scruff? And it turned out they found several more bits of scruff that, when they zoomed in on them as they came around, also had these pulses hidden inside them, these amazing pulses. And it is at this point in the story that the astronomical community, for the most part, said goodbye to our friends the aliens. Because either 4 different alien civilizations, intelligent ones, developed independently, and then all decided this was the best way to get in contact. Blinky method, for sure. Or we've got a really crazy advanced civilization. They figured out how to spread these signals all over the galaxy and send them to us, and they still thought that was the best way to say hi. They couldn't think of anything better than blink at you from all over the galaxy, and that seemed pretty unlikely. Maybe not the first aliens we want to talk to. So this is when the aliens were let go, and they moved on to the next question. And to remind you, what we've got left are stars, white dwarfs, neutron stars, and black holes. So the next question that they asked is, how long are the pulses? So and by how long are the pulses, I mean how long from right here when it jumps up to when it has jumped back down. And this is important not just for time purposes, but also for space, because for a reason that's really cool and I can't fully go into, but please ask me about it later, how fast this is translates to how big the object can be. And that is because of the finite speed of light and the shape that most astronomical objects tend to take, which is a sphere. So because of this, they were able to determine that the radius of the object couldn't be more than about 3,000 kilometers. Now, if you asked me to run 3,000 kilometers, I would tell you that is a very long distance. But when we're talking about astronomical objects, that's a little under 2,000 miles, which is less than from here to Chicago. It's also only 0.4% of the radius of the sun. So on scales of even our solar system, this is pretty small. And in fact, trivia question number 2. What do you think they ruled out with this? I will take hands. Someone in the back. Black holes. No, it is not black holes. All right, I'll take another hand. Let's go over here. Yes, it is stars. So if it's 0.4% of the radius of the sun, that's a lot smaller than the sun. Our sun is not even that big of a star. So any stars pre-death are going to be too big to create a pulse that happens this fast. So finally, there are 3 objects left now, as you can see. We got them, but it's fine. They are white dwarfs, neutron stars, and black holes, those stellar remnants. Now, this is the final knockout round, where we have to actually ask, how is an object that is not an alien and does not have a consciousness and cannot build something to make such a perfect pulse? Is that the train or is it just something? Okay.
It's the train.
Ready? Everyone, choo-choo! All right. It's going to keep going for a while, though. That's how this train works.
It's not too bad yet.
We got the worst of it.
Yeah.
We started.
There we go. There it is. Okay. I think you're good.
Okay, we're good to go. So, final knockout round, we have to actually look at how an object with no real intentions just accidentally happens to be making this perfect pulse. And there aren't that many mechanisms for doing this. But to explore, we're going to have to explore. They were exploring each mechanism and looking at basically the biggest and smallest number, because you have to be able to fit all the pulses. And I'm not sure I said this, I definitely should have, but they were looking at how fast it pulses, this time in terms of the time between the pulses right here. So that ranged from about 1/4 of a second to a little bit over a second. And the only options for this mechanism were really pulsing itself, kind of like vibrating, spinning, because when you get circular motion, you have this repetition of the circle over and over. And similarly, another way to move in a circle is to orbit something. So they looked at orbits, and you may have heard that black holes are very, very dense, and not even light can escape. So you may have been wondering, how is that going to work? Is light just going to magically jump out of the black hole at us at a very regular pulse? And the only option for the black hole is really that black holes can accrete matter, and as we've seen in the news recently, that creates this sort of glowy ring around here when the black hole is eating up all this matter. And the idea with the black hole is, well, if you just have one little blob somewhere and it rotates around and around, you could get a pulse. The problem, which many astronomers will tell you, is that black holes are extremely messy eaters. And so as soon as the matter gets in here, they're going to start throwing it every which way. It is going to get smeared across everything. That is why we tend to see rings. And so once this was actually considered, they also had to say goodbye to the idea that this was coming from a black hole. And in terms of the 2 objects left then, white dwarfs and neutron stars,
sorry.
We're still here.
Sorry.
It's okay. So when these objects spin around in orbit, they have other ways of making the light. But when they orbit each other, basically they get faster and faster, as you can see. And eventually, if they're going faster and faster, they're going to merge. And to be orbiting once a second, they'd already have to be quite close together. So it wouldn't be very long until they merged, and they would be getting faster. When they went back and looked, there was no evidence that any of them had merged into one, and they were actually getting slightly slower. So it looks like orbiting is probably not going to create pulses every 1/4 second to 1.33 seconds. But next, they looked at pulsations. Everyone, I'm sure, was thinking this was great because that's why they called it a pulsar. But we're going to look at pulsations, and pulsations are kind of like, they work with astronomical objects the same way it works playing an instrument. It's just dictated by the characteristics of the instrument. You can't make the same sounds on a violin that you can make on a double bass just because of how they're built. So for a white, and they also have fundamental frequencies. And unlike when we play instruments and we put our hands all over the instruments to make all the crazy sounds, no one's putting their hands on the stars, on the objects out there. So generally, when they get excited, you're going to hear the fundamental frequency. And you can't change that frequency. So for a white dwarf, that frequency means that they pulse about every 2 seconds, which is a little slow for what they saw. And for a neutron star, they are like the tiniest little violin. They pulse every millisecond, which is way too fast for this. They can't go any lower. So pulsations also weren't working, and now they might have been getting kind of nervous. What's left? Well, we still have, back one, sorry. We still have spinning. They still had spinning. And the only limitation on spinning is that an object can only spin so fast before it flies apart. I don't know if any of you did spin art as a kid. I did. That's what this picture is of. Not my spin art, but someone's spin art. And what would happen is you spin the paper around, you put the paint on it, usually somewhere near the center at the beginning, and it flies way out to the edge, because that's just what happens when things spin. The only reason that every spinning star has not flown apart and that we are still on the Earth even though it is spinning is because there's gravity holding us on. But if the Earth spun fast enough, we would fly off. So this is the limitation for both of the objects left, is that if they go too fast, they won't exist anymore. So we are in the final trivia questions of the night. How fast do you think a white dwarf can spin before it becomes stellar spin art? You can think for a little bit. I'll take hands whenever you're ready. Anyone? Just go with your heart. All right, we got someone over here. Yes. Much less. Not quite. No. We got another guess. That was much less than 1 time per second. They can go a little faster than that. Also back here. B. Just under once a second. Yes. And that is a problem because we have this 1/4 second pulse right here. If a white dwarf were spinning that fast, it would quickly just become stuff hanging out in space. So this is too slow. And now they had to investigate one thing that's left, neutron stars. And if that doesn't work, maybe they're going to have to go back to the drawing board, consider some aliens with really weird communication styles. But let's see. Final trivia. How fast can a neutron star spin before it becomes stellar spin art? Yes. Hundreds of times a second. Ding, ding, ding. Yes, and that is great news for the astronomers because that is plenty fast enough. That translates to about once a millisecond or so, and that is plenty fast enough for the pulses here. Since then, we have also seen pulses go up to about that limit since more pulsars have been discovered. But this is when they finally came to the conclusion that pulsars were rotating neutron stars. And may I remind you, before this conclusion, no one knew that neutron stars existed. All of a sudden, there's 4 of them, and they're blinking at us constantly. So this was a huge deal in physics and astronomy. And in fact, Hewish and his colleague Ryle were awarded a Nobel Prize for this discovery in 1974. It was so important. But I hope you're enjoying the spelling of Nobel as much as I am. This was a common jab at the time because you may notice Jocelyn Bell, the one who saw the signal and made sure everyone was paying attention to it, is not included in this award. But fear not, this has a happy ending. In 2018, just 6 years ago, Jocelyn Bell Burnell, that's her full name now, was awarded a special breakthrough prize in physics for her discovery of pulsars. And being well into her career, she said, I don't really need the $3 million from this prize. I think I'm going to start a fund to help support underrepresented graduate students in physics so that more of them can come in here and make amazing discoveries too. So that is the happy ending to our story. And to wrap up, I just want to give you a few more things to think about or remember from this. One is just so Jocelyn Bell. I mean, her whole career, Belle Burnell. She has been making amazing contributions to the fields of physics and astronomy, right from when she was a graduate student making this amazing discovery, to all the way into the present where she is supporting future astronomers in the field and their amazing discoveries. So tell everyone about her if they don't already know. The second is don't discount the theoretical objects, because we would also figure out, only in 2015, that black holes are definitely also out there. And just because we can't see it, or we've never seen it before and no one's sure it's real, doesn't mean it's not real and it's not what we're seeing now. And that's pretty exciting to me. Also, something that Jocelyn Bell herself has pointed out, Belle Burnell has pointed out herself in several interviews, is these days, our telescopes bring in huge, crazy huge amounts of data. And to sift and sort through all that data, we tend to use computers that we give algorithms, we tell them what we're looking for, and they help flag things for us. And if that had been how they were sorting through the data from this radio telescope when she was a graduate student, who knows how long it would have been before someone saw the little bits of scruff. Who knows how long it would have been before we figured out that neutron stars were real. So I think this is cool because it means that, you know, even though computers are getting really intense and there's all these talk about AI and everything that we use them for, humans are still really necessary with our insights and our curiosity and our judgments. We're necessary to science and to making the most exciting and unexpected discoveries in our field still. Finally, I will leave you with this. You might think, pulsars, really cool, great, figured that out. I'm sure you figured out how to deal with all the blinking objects since then. I'm sure that's a done field. Not true. Mysterious blinking objects are still quite common. Be prepared to ask these few questions several more times in our lifetimes. In fact, I'm just gonna leave you. Oh, hit a few more times, sorry. I'm gonna leave you with some headlines from the last 4 years. 2 more, yeah, there we go. These are just 2022, 2023, and one's from 2019, but we've got, in these 3 headlines, hundreds of mysterious blinking objects that have come through in the last couple years. I'm sure there will be more, and as this subheading, which is hard to see from here, points out, it says, scientists have no idea what it is. Well, now you know that we do have ideas. Most of them are probably wrong. But if you're interested in mysterious blinking objects, it's still a very active field. You should definitely get involved. There's plenty left out there for you to discover. Thank you so much for listening. Yeah, do we have questions? Any follow-ups? Any hands? I see one back here. Yeah.
Thank you for the great talk. I have a question about the timeline. So, like, whenever the scientists were sort of eliminating these possibilities, how long did it take them from whenever they saw the signal to be like, oh, we actually have something here?
That is a great question. They were asking what the timeline was on figuring all these things out. I mean, did we take 40 years and we just figured out, or 75 years almost it's been, actually, but did we take a really long time to figure this out, or was it pretty quick? And the answer kind of depends. I mean, basically, there was a paper published that gave a lot of these, that went through most of these arguments in 1968, so about a year later. But some of the stuff, like just making sure that it was outside of the solar system and looking for more signals, happened pretty quickly. Also, cool fact, when they looked for more signals, other people started looking back at their radio telescopes to see more signals, and pulsars became like this really rapid discovery because it turned out we'd been observing them for a while, no one had noticed. But yeah, I would say year-ish in total, but some of them came faster than others. Awesome question. Do we have any more? Over here.
Does that beam of light that's created have to be like focused directly at us to see it?
Ah, okay. Does the beam of light that pulsars create have to be focused at us for us to see it? It doesn't, I mean, so it's got some width, right? And the reason it blinks is because we see it sweep around and around. So it has to point toward us somewhat. There is like a range in which we can see it. So there could be more that are just pointed completely the wrong way for us to see. Awesome questions. Back here. Interesting. Very broad question. It was pointed out that Jocelyn Bell didn't have the kind of internet we have today, the kind of internet or the kind of interconnectedness. And did that make it easier or harder? Does that make it easier or harder to follow your passion and go down this rabbit hole maybe and say, hey, I believe in this little piece of scruff? I mean, I guess really that's a question for Jocelyn Bell. I am not a person who has grown up significantly without internet. Fortunately, I cannot speak to that as much. I don't know. I'm sure there's more criticism, but also, like, it's way easier to find out about these things and get excited about them. Before, you have to have the right person, like, come through your town and give a talk. Now, we can see these online. We can read the cool headlines. I cannot give a definitive answer there, but I hope that the things we're putting out there are making it easier for people to get excited about science and decide to pursue it. Awesome. All right. Any more questions? Yes, over here.
Thank you. Great talk. Appreciate your time. Great. So if a neutron star generates pulses, but the neutron star is made up of neutrons, which has no charge, how does it generate these pulses?
That is an active field of research, my friend. Yeah, although they do have protons and electrons, they just have a lot more neutrons than regular matter that we tend to interact with. Highly neutron rich, but there are protons and electrons. We believe that has something to do with it. Yeah, but it's interesting. It's really, really big magnetic fields are involved. That we know that's true. We just don't really know how exactly they're involved. Come ask me in like 5 years. Maybe I'll have some cool results for you. Yeah. All right. So many great questions. Is that it? You got any more? I could be here all night, but you probably want to hear the next speaker. Here we go.
All right. Thank you, Maria. Excellent talk. Yes, we did that. Thank you. All right, just a couple reminders before we go to intermission. Reminder that we have merch over here. For those of you that answered the trivia questions correctly, we have a little freebie for you over here. There is also, courtesy of AAS, there is a bunch of free stuff over here as well, so come check that out. Merch table should be hopping in intermission. We will be back in about 20 minutes. It is currently 8:01, so let's call that an even 8:20. 8:20, we will be returning. Thank you very much, and don't forget to tip your bartender. All right, and we are back. So we will have our second talk by Fuda in just a little bit, but right now we are going to turn to Jackie and Danny to find out what is happening in the universe recently. Jackie and Danny, take it away.
Woo-woo!
Ooh, fancy microphone. The what is on? Yes.
Yay!
Okay, hello everyone. My name is Jackie Champagne. This is my counterpart, Danny Krolikowski. We are postdocs at the University of Arizona. I also go by What a Merger Jr., which is very funny, and Danny goes by It's a Trappist, which is also very funny. Thank you. This is the Comedy News Hour. Welcome. Tonight we bring you News Light. Simply nothing is going on in our universe right now. I scoured and scoured to look for news to bring to you. Nothing's going on. The James Webb Space Telescope is happily chugging along. That's excellent news. Producing new discoveries about young stars, planets, galaxies, you name it. We don't have any real updates on any current or near future missions like Euclid or the Roman Telescope. Nothing's really happening. So everything is status quo. Here at the University of Arizona, we are gearing up for the new semester, and many of us recently attended the American Astronomical Society meeting in New Orleans. So there was no doubt much hurricane-themed merriment going on. Actually, I wasn't invited to that conference, but if you were there, I'm happy for you. Okay. So in the hangover of the holidays, we bring you some mundane news. Neptune simply is not blue. Bummer. Okay. So most of us are probably familiar with the brilliant ocean blue of Neptune as viewed by the original Voyager 2 mission back in 1989. And at that time, our picture of the outer solar system included this greenish blue Uranus and a much deeper hued atmosphere on Neptune. However, new data from Hubble and the Very Large Telescope, which is a real facility, new data has revealed a slight hiccup in our bookkeeping. The original Voyager images were edited for the public. Oops. So, for astronomy research, I would like to set the record straight. So scientists always need to edit images. The data comes down from the telescope in like a jumble of numbers, and it really doesn't make any sense. Something has to be done about it. And we frequently get asked questions like this when we do public events. Are we really seeing something, or is this Photoshop wizardry, like when you see something from James Webb? The answer is somewhere in the middle. So for instance, JWST sees in the infrared, so our eyes can't see infrared. So we can use shorter infrared wavelengths to represent blue and longer wavelengths to represent red, and then you create a commonly used RGB image like what you see on your computer. So you have layers of red, green, and blue to represent the different wavelengths. And so the image enhancement involves teasing out certain features. So when you see these beautiful images of nebulae and other galaxies with James Webb, some enhancement has been done there. So for the Neptune press release images, they were trying to get that cloud to pop out right here, this cloud. And that involved really turning up the blue filter until it looked like that. But it didn't look like that from Voyager. So the data never lies. That is an image of Neptune, but the color balance up for interpretation. So apparently the various captions across these old-timey print journals and print newspapers, a foreign concept to most of us that were born after the Voyager 2 mission, made it clear that Neptune was indeed a false color image, but this has all been lost to Father Time, and now this is the image that is in all of our textbooks. So anyway, these new images from the Hubble Imaging Spectrograph and the MUSE instrument on the Very Large Telescope in the very large country of Chile reveal Neptune in photo filters that are closer to what the naked eye sees. So perhaps if you are an amateur astronomer with a fancy telescope, you've already beaten me to the punchline, and you already know Neptune was never this color. It's actually green. The new images still reveal some interesting characteristics about both planets, though. Neptune is still a bit bluer than Uranus, which the lead authors attribute to a thinner haze layer in its atmosphere. They also learn that the atmosphere of Uranus changes colors throughout its year. So when one pole is pointed towards the sun during the summer and the winter, it appears greener, but it takes on a bluer tinge when the sun is over the equator. This is likely due to an icy haze around the poles, which contains less methane than the atmospheric composition near the equator. So this has taken decades of atmospheric modeling to calculate how light interacts with gases and aerosols, revealing some really cool information about the seasonal changes. So Mr. Blue Sky is a bit of a lie, but don't despair. It's actually pretty cool that we're learning about atmospheres on other planets and that we can actually do this from ground-based telescopes. So yeah, that's it. That's happening in the universe. And maybe Danny has something more uplifting for you. Thank you.
Woo!
Yeah, I guess they're different. Sure. Hello. I think possibly for the first time ever in doing news in Austin and here, I'm actually talking about something kind of close to the research I do. I guess I do care about astronomy sometimes that I do myself. Yeah, so I think we can all kind of remember maybe how fiery we can be in our youthful days as a teenager. And that is certainly true for exoplanets also, highlighted by a new discovery that was announced actually at the AAS last week by a team that found a new small exoplanet, HD 63433d. That's honestly less numbers than you normally have to deal with. And what's unique about this planet is that it is quite young, and it orbits its host star extremely closely, about 10 times closer to its host star than Mercury does to our sun. So, you know, I mean, I've talked about close-in planets before here, so like, why is this interesting? Well, the fact that it's young is really, really cool. Why? Well, we still don't really know how planets form and evolve entirely. There are a lot of processes going on that we have to disentangle and try to understand. And to do that, we need to see the planets as they're evolving. So we need to see baby planets, toddler planets, teenage planets, all around, right? If you like measured the height of a 2-year-old and then like didn't, you know, observe them again until they were 18 and you measured their height, like, okay, they got taller, but like how? I don't know, right? We could do that with planets. You could see a baby planet and an adult planet and say like, oh, it got different, but we don't know how. So we need to find young planets to understand. So this planet, or this star, HD 63433, is about 10 times younger than our sun. It's 400 million years old, which might not sound particularly young, but it is quite young. Probably about young preteen, let's say, in a planet's maturing phase. So this was done by the Time Collaboration, whom I've worked with before, the Transit Hunt for Young and Maturing Exoplanets, which I think is probably one of the better acronyms I've ever heard. I'm proud to know who made that acronym. And so they find young planets by looking at transits. So they look for planets as they pass in front of their host star and block out some of the light, and you can see a little dip. But this is not like an easy old planet that like, oh, that's a transit, great. Young stars are a mess. So this plot on the right, all of these wild wiggles are from the star itself. So the star is noisy at about the 1% level. The transit signal of the new planet is 0.01%. And so you have to fish that out of all of this noise. I couldn't do it, but they could. So that's really, really cool. Like I said, it also orbits very close to its host star in every 4 days. So it's really, really hot. Normally, when I've talked about close-in planets, they're around M-dwarfs, which are really small and a lot cooler than our sun. But HD 63433 is about the same size as our sun. So the dayside temperature of this new planet is 2,300 degrees Fahrenheit, which is approaching the melting point of steel, which, I don't know. I mean, for some of you that are cold tonight, that might sound good, but maybe a bit too much. But for this planet, with its very hot dayside temperature, unlike, you know, a hot-headed teenage human who outgrows maybe their tendencies, this planet will be hot for the rest of its life. Cool. Thank you. This microphone is so nice.
All right, thank you, Jackie and Danny. And now for our final talk of the night, I would like to introduce Fuda Nguyen. He is a colleague of mine also at the University of Arizona, and he is going to be talking to us about space travel by words. Fuda, if you don't mind, take it away. Oh, we're going to be passing around things as well, so be ready for that.
Hello, people. My name is Fuda Nguyen, and Nguyen is a Vietnamese last name. So I came from Vietnam over to Tucson to do my grad school here. I'm a second-year grad student over at Planetary Science, working with Daniel Pai on exoplanet atmospheres. In my free time, I write poetry, and to my advisor dismay, I have zero citation in the things that I write. And I don't make any money off of it, so also to his dismay, to my relief. So I'm just gonna wait for Nick here to help me pass out the hands out. I'm not gonna be reading all of it because time constraint. For some of these poems I've never read out loud before, so I'm not sure how much time that would take. It'd be nice if I can do all of them. But I'm just gonna try to do 3 of them first, and then we'll see where it goes. Also, can people hear me well? Okay, cool, nice, thank you. Okay, looks like we're good. So the first thing that I'm gonna read out of here is Planet on Other Stars, number 2. So that should be on the first page, just for your references. Planets on Other Stars. How would alien treats their own kind? Evolutionary miracle or endless struggle for more? Planet on Other Stars unknown 30 years ago. Mother was 20. Country war ravaged, dirt poor, small village. She went to Saigon, see a movie for the first time. Even thinking about it is a privilege. On the day we do find strange life out there, I will be missing my grandma, her garden soil, warm and moist. Be blissful, I'm not alone in space. So easy to tunnel vision in the ivory tower mission, thinking about planets, stardust, and chemicals of life out there. But never forget where you're from. Remember to have a place to call home. Carry with you love and trauma of your family, soil that bored you, tropics, plants, leaves, humidity. One day you will find beaming earths, flora, fauna, in your elusive search for planets around other stars. And now, you'll have more reason to feel small. In eternity, massive cosmo unending, to not be alone, stargazing. Thank you. Okay, so that was actually quicker than I thought. So, well, I'll take it back. Maybe I'll read all of it. Okay, so the second one is called Time. Just before I read, I'd like to talk about it a bit. Time is such a weird thing to me. The perception of it, at least. We all know, like in terms of physics, it just go the rate that it always does, constant, except when you're near a black hole or like a very massive stars. But on Earth, it's pretty constant most of the time. But I had to work on a paper revision yesterday, and it feels like I spent 15 minutes on it, and it's like, oh, 3 hours passed. Oh, I don't have to work anymore. So this poem is partly inspired by that. Time. Time in English is a physical object. Take your time and shove it in your pocket. How much time do you have? Are you out of time? Còn thời gian trong tiếng Việt là dòng sông chảy không ngừng. Còn bao lâu? Hết giờ chưa? Tới giờ chưa? I shove a chunk of time in my hands. Time to see and time to breathe. Breathe in, deep breaths. My time flows like orcas. Time is an ice cream shop. Time dizzying array. Time cold and condensed. But time can also be oceans and dry seas. Time can be rice paper, wet, soak in water. Time lets me graciously postpone my death. Is time rolled off like a scroll of paper? Or is time ripe for the spring time? Time will flow over you and me like tsunamis into beach huts. Try stopping time and it will stop you. So is time physical? If time can fly, time can run, time can be exhausted, time can be wasted, time can be found, and time can pause. Time can be taken, time can be in and out, time like streams, time can be frozen, time can flow, or is time water, is time muddy, like a piggy brown puddle, is time crunchy Pop-Tart, or is time hardened concrete impervious to the flutes flowing? Can I hold time in my hand? Watch it slips through the crack, carry away by the wind, into time far away. Your time, my time, is it all gone? Gone where? Gone when? What time? Which minute? Which hour? Time in the human language is a one-way flow. Take your time and stretch it forward. But how much of past time is not visited? How much of future time has already happened? Has there always been no beginning, no ends? In silical eternity, is it time to end and begin all over again? Thank you. The next one is on page 4. It's called Avatar 2 is great. You should go see it. Is science ultimately good? Or is it just a tool for expansion, exploitation, destruction? Finding alien life being a part of history, only to see them getting destroyed? Beauty and ugliness always coincides. The beautiful songs of the intelligent whales clan, cross-species friendships, the fire torching across the forest, burning zillions bodies, fauna, the aquatic glow of the biosphere acting as one in unity, the disgusting cruelty of metal arrows shooting through fleshes, gutted, bloated, the power of cinema and ruptures, capsulates, engulfing every senses, makes one question their moral stands, good and bad. Will finding alien life leads to demise or joy or ravage or bliss? The next one is called How to Turn a Sphere Inside Out. And this is actually a YouTube video. It's really fun. You can go see it. It talks about topology and how you can turn a sphere inside out, but you cannot turn a circle inside out. So this poem was partly inspired by that. It also touched on one of my great shame is that I'm very sorry to say, but as an astronomer, I have just very bad math. I'm terrible at math. It's never been something that I'm very particularly strong at. But for some reason, topology just worked for me. It's like, I'd like thinking about geometry more than I think about algebra. Yeah. And my mom, who is like a small business owner, she completely, she just takes shame at this. She's like, you cannot do this 20% tax in under a second. You're shame. You're such a sort of shame. Mom, you're right. You're so right. I'll take it. How to turn a sphere inside out. When the surfaces can cross and pass through, but knots can be made infinitely small, else the shape breaks into pieces. How to fold the sides into one another and join their faces to make a finite space which is also boundless, traveling in never-ending loops. How to be at two places at the same time, quantum tunneling between the deadly yellow of the desert and the knee-deep flooding of the tropical monsoon. Spiky flora doesn't like the color green, just as the combustion engine doesn't like to be choked by water. How to join two fluids of different densities, shake it, make it form zillions of little bubbles that will only eventually merge into its own kind, one oily and one watery, keychain in acrylics, forever separated by its contact surfaces. How to inflate an airless balloon, love the little things that function as a livelihood, maintaining normalcy in a wage slave economy, convincing us that there's no alternative, but sanity can be stretched so thin. How to defy geometry, how to behave against the quantum law, how to draw divergent fluids against one another, how to self-medicate while self-isolating. I could give the first question to the mathematician, the second to the physicist, and the third to the chemist, the last, your pick. But I'd rather give them to all of you. But I'd rather give them all to you. Since when has anything stopped you from questioning? So keep asking, my friend. Can you not rage at this absurd world? Can you backtrack through time and space? Can you maintain sanity? Can you separate your mind and body? Can you turn a sphere inside out? Can you be at two places at the same time? Can you fold yourself into another? Can you love what is a lost cause? Can you love yourself, others, the world? Can you love? Can you turn a Taurus into a coffee mug? Thank you. And I have two other ones. This one is called The Day We Walk into the Earth. And it is partly inspired by Tucson. Just so you know, I love Tucson, so don't get me crap if I finish reading this, okay? The day we walk into the Earth. Amplitudes describe the degree of variation a time variable function can experience. Amplitude then describe how are you likely to die from climate change. The drought has been onward for 100 years. The flooding has been unrelenting for 100 summer. Predicting the future, monkey business, futile device. Tucson in 1,000 years, when all trees have burned, tears have evaporated, fundamental fluids sail from sea to sea. In wondrous vastness, they witness the most beautiful monuments, valleys, planets, waves. On the tallest, driest desert, on the only known planet with life, the universe gazed back at itself and its destruction. If we're all marching towards oblivion, so what? It's just another age of reformation, evolutionary creation anew, cyclical eternity of planet Earth reinventing herself. The end is the beginning. We walk with pride into a new demise. Let us be grateful. Let's Gila monster and ravens build civilization, and let us invincible monkeys locked up for the last time. Thank you. And I have a last one for you guys tonight. It's called 5,328. So this number, I believe, by the time that I wrote this poem, which was in October 2023, was the number of discovered and confirmed exoplanet candidates from the NASA Exoplanet Archive. So it is something I worked on, and I spent a lot of time thinking about it in general. There's no less than 5,328 exoplanets. No less than 5,329 balls of the heaven, ours included. There's hot balls, there's cold balls, there are inflated balls with choking air, there's crusty ball with rocky shards. There are cloud balls with cyclones and eyes of the storms, many times the size of the Earth. There are more balls than one could fill their days with, to study, to observe, to excite their imagination. Worlds upon worlds upon worlds, in the vast number of games of the galaxies. Yet, out of all those great numbers, only one is known to have life, so far. On this ball of ours, the sky is blue and so is the ocean hue. Here, the cells aggregate in great enclaves to make biological machines, livers, kidneys, and brains. Here, a curious incident called intelligence took place. On this ball, a two-legged advanced conscience asks itself, how do I know? How do I see? How do I know I have weight and mass? Why do I see the earth curving a bit when I fly up high? How can I fly? On this ball of ours, the forests glow in green and red, so red even the human eyes couldn't see. There, molten iron rotates upon itself deep in the rocky sphere. There, invisible electromagnetic breathing of the earth propagates itself through space and time, where an advanced conscience asks themselves, how can I hear these humming waves pulsating around me? Why is my feather black? What are those glowing dots in the sky? And what are those metallic boxes moving on the ground? Can I crush this nutty thing with them? And so the black feather magnetic sensing two-leg flying intelligence dropped the nuts she held in her Cambrian claw-like foot. It fell onto the concrete surface and is promptly crushed by a 2-ton moving vehicle. And just like that, our feather friend feasts on her lunch, without forgetting to ask herself, how did I know to open up my stubborn lunch? How did I know lunch? How did I know? How do you know? Do you ever wonder why your arms move the way it does, seeing a non-celestial leather ball flying at you? As you reach out to catch it, your fingers and joints are making movement faster than neurons can communicate. Do you ever wonder, why does your heart beat? Why does your eardrum rings? How does certain song makes you happy or sad? Why does the sky glow red and the moon glows circular orange? Why does the crow drop her stubborn nuts on the roadway? And how does the celestial sphere spots its own face with dots of light eternity away? With soft lights, with blue lights that shift to red sometimes, lights from 100,000 millions, billion, trillion, zillion centimeters away. Lights emerging from compressing nucleus, light that could not brighten up a forever expanding room, beam reflected, scatter and bent. Light that never stopped and literally cannot stop. Light that might come from one of no less than 5,398 exoplanets. Somewhere in this unending darkness, could there be a jet black feather conscience flying, spreading her feathers on another crusty rocky ball with a slight touch of wetness on its outer surface? Could she be looking at one of those light dots, wondering if there's life too?
Woo-woo!
Thank you, and that's it. That's much shorter than I expected, right?
Oh, good. It's great.
Thank you again.
All right, thank you, Fuda. And with that, that puts a cap on Space Drafts 94. Just a couple of reminders. We will be back here at 7:30 p.m. Mountain Standard Time on February 20th. a quick reminder to come over and visit us at the merch table. Come get some of our merch. There's a bunch of free stuff over here. There are also eclipse glasses if you're getting ready for the April 8th eclipse. And once again, thank you all for coming, and we will see you next month on the 20th.
Woohoo!